I'm quite glad to see so many people here. I was expecting that title would scare everybody off. My name is Paul Harwood. I'm these days an independent software developer, and I'm not even that much of a software developer anymore, semi-retired. And I'm not here to sell you anything. I said up front, I've got nothing to sell. As the introduction said, for the last 5 years, I've been working on and off in understanding GIS data or visualizing GIS data in virtual reality. And this is part of a project called the Verges project, which is still a project, it's still ongoing, it's open source and also product, but it's been a bit quiet for the last year or so. But as part of this, as part of trying to understand what GIS means in true three-dimensionality in virtual reality, and I apologize for the video, I'm a terrible walker. I walk up and down. I'll try and stop doing it. Trying to understand what 3D data sets mean in true 3 dimensions and in virtual reality, I have come to a terrible realization, which is that the foundations of GIS are wrong. And I've come here to tell you all that the foundations of GIS are wrong. And that's a very scary thing to do to a group of people like this. If you look at them in 3 dimensions, we need a new ontology. And it's not just a layer on top of what we talk about in GIS. It's actually a fundamental change. And this realization actually came about whilst talking about 3-dimensional GIS at a conference called Computer Applications in Archaeology conference, with some people who are trying to do it as well. And we were just sitting there trying to make the terminology work in true 3 dimensions, and just getting more and more and more abstruse about how we make the terminology work and how we make the data sets work. And I kind of come to a realization we have to change the foundations. I have to say that this is by nature of a postcard from the edge, because I'm out there at the edge trying to do it in virtual reality, coming back to you guys who are perfectly happy working with rasters and vectors and thinking about rasters and vectors in QGIS and saying you're all wrong. But this is a warning that the foundations are shaky. And the other part of this is I'm discussing concept here. I'm not talking about formats. I'm not talking about processes. There is actually nothing that you can do in what I'm talking about that you cannot actually do with the current systems. It's just the terminology forces conceptual acrobatics that makes thinking about it difficult for people. So, where do I start off? At the moment, we have raster and vector. Yeah? Raster and vector concepts, not formats. We have raster and vector concepts, both of which have been brought in because GIS started out with mapping, and because mapping started out with computer graphics and taking a picture of a map and drawing on it. We've basically taken the formats and the concepts, the ontology from computer graphics and ran with them. These have been grandfathered in, and they're the problem. If we think about data sets in terms of rasters, or if we think about data sets in terms of vectors, we fundamentally cripple our understanding in 3 dimensions. Rasters, to start with, obviously, they're an image. It's an image, it's a 2-dimensional data structure. It has pixels. There's no definition of whether a value is where it is in the pixel. There's no definition about whether it's a vector or a scalar. There's no definition about whether it's a point or a line or a volume. All of this is not in the format. Also, it's planar. Planar is not a problem if you're working on the screen. If you start putting it into true 3 dimensions, planar has a lot of problems. It might be planar in one projection, not in the other projection. The actual position of the data that you think is in the raster is going to change depending upon your projection. Might not be a problem if you're or working on a very large scale. If you're working in terms of smaller scales, that could be a big problem. So there are fundamental problems with rasters when you try and use the concept within 3 dimensions. You'd think vectors might be a lot better. And you see a lot of vector formats quoting 3 coordinates and saying they're 3-dimensional. The problem is the definition, the definition of a vector point in 3 dimensions is quite clear. The definition of a vector geometry in 3 dimensions is naturally not. To give you a rather extreme example, which is where part of this conversation started from, if you take a polygon in a projection with 3 coordinate axes, you'd think it would define a 3-dimensional shape. But unless that polygon, I'm going to get quite technical some of this, so sorry about this. Unless that polygon is planar in the projection you're using and is orthogonal to the coordinates in the projection you're using, depending on how you render that polygon into a shape in 3 dimensions, you're going to get different shapes with the same data. Not a problem probably if you're drawing them on a map. If you're creating a 3-dimensional object within virtual reality relative to a coordinate system, which is probably effectively transverse Mercator, you're going to get data in different places. Again, maybe there may not be a problem, but it might be a problem if you're doing very small scale stuff. Some cases, that polygon, if it's rock formations, that polygon could be miles across, in which case the error could be hundreds of meters. That could make quite a difference. I have to say that I so have, from what I saw, and this is actually a slide from last year or the year before, I so have stated that the current SFA is not a 3-dimensional FSA, not a 3-dimensional ontology, and are working towards it. I just think trying to fix the SFA is placing complexity on top of complexity. So what does a true solution look like? We need to build it bottom up to be geometrically embedded in a 3-dimensional space, or possibly a 4-dimensional space, or a 3+1 dimensional space. We'll come to a lot of these as we go along. We need to have a single conceptual ontological representation for all datasets, so that the practitioners aren't actually spending a lot of time, shall we say, converting data from raster to vector, or from volumetric to non-volumetric. This should all be transparent to the people trying to manipulate the data. We need accurate representation of topological spaces, regardless of within a 3-dimensional or 3+1 dimensional environment, regardless of the topological dimensions of the shape. So that means accurate representation of points, zero dimensions, lines, one dimension, polygons, 2 dimensions, voxels, 3 dimensions, eons, 4 dimensions. As an add-on, which I won't go into any more than just a bullet point here, the data on that should always be represented as some form of tensor, some form of multi-dimensional data. So you can have vectors, you can have matrices as data on every point. But that's just an add-on. I won't discuss that any further than it says there. And obviously, we've got to be able to completely integrate existing data sets. This is where it gets the most abstruse. So hopefully we'll get through this one. Geometrically intrinsic embedded in 3-dimensional space. And mathematically means it needs to be a topological manifold. A topological manifold is a mathematical object or concept which represents an n-dimensional space, is locally Euclidean, and is flat and complete. I'm approximating here. If we want to go into more technical language, it's there. So that's what it means when we say it's embedded in three-dimensional space, and it could be multidimensional. What you do within mathematics is that you then do a process called projection, which turns it into a topological chart. This is obviously the generalization of the process that we all know about, which is you take data and you project it and you have a chart, which is a map. But this is a mathematical generalization, and it means you add axes to the data, to the topological manifold, so you can manipulate it, and it can be multidimensional. Once you add a projection, once you make it into a chart, it then becomes geometry. So you've gone from topology to geometry. If that projection has geographical meaning, if the sort of projections that we're used to dealing with, then not only do you have geometry, you also have geography. So now we have a geographical space, which is arbitrarily multidimensional. But to use it in GIS, we have to take that geometry and we have to discretize it. We have to digitize it. And if you digitize a geometry, the term for it is a mesh. So this is why I say the data format, the data structure, the ontology, I should stop using the word format, the ontology that we need is a mesh. And it's this mesh as a discretized geography, which is defined in terms of a topological manifold of n dimensions. To make it slightly less abstruse, and if you want to think about this in terms of a sphere. A sphere, a pure sphere, is a two-dimensional manifold in three-dimensional space. So it's two-dimensional. You can the surface has no width, but it's represented in three-dimensional space. So in fact, we do this all the time. This is a generalization of that conceptual leap, taking a sphere and saying it's two-dimensional. We can measure distances along the surface, but not up and down. But it's embedded within three-dimensional space. And we can have these topologies of any dimensions. When I talk about topological dimensions in this presentation, generally, I talk about M rather than D, just to make sure it's a topological, it's a manifold dimension and not the space dimension. So a point is a zero-dimensional manifold within three-dimensional space. A line or an edge, meshes are a subgroup of graph theory in maths or network theory outside of maths. So therefore, we tend to talk about edges and faces, similar to Gabriel. So an edge is a line bounded by two nodes, can be directed or undirected. A face is a planar surface within the mesh. A volume or voxel is a three-dimensional object within the manifold. And when we get to 3+1, we tend to talk about epochs. This is kind of a digitized version of time. You see this? Importantly, as I say, all of these objects, or even all of these meshes, are three-dimensional. Even if they're one manifold dimension, they're embedded with a three-dimensional space. If they're 3+1 manifold dimensions, they're embedded within three-dimensional space. So we now have a fundamentally three-dimensional understanding of GIS data. Also, when we're talking about our ontology, our conceptualization, we want the data sets to be able to have all of these objects at the same time, which is, again, one of the problems with the existing conceptualizations. You can have a data set of points, or you can have a data set of vectors, or you can have a data set of polygons. But if you want a data set of points and lines, if you want a data set of heights and slopes in each direction, you then end up with different data sets rather than having them all together in one data set. So it's an added value to be able to have them all at the same time. Ooh. So that's primarily what I'm proposing. I'm proposing, that's before we get into that, I'm proposing every data set, every GIS data set is one of these. I'm now going to spend 5 minutes going through proving that the legacy data set, not proving, suggesting that the legacy data sets all match this. Let's start with the vector formats. It's simplest enough. If they're SFA, they're made up of points or lines or polygons or tins, or even some of the more obscure ones which nobody ever gets to use. All of these already exist in this ontology. So therefore, I propose that any vector format, any SFA compatible vector format can automatically be turned straight into a mesh. It doesn't necessarily work the other way around. You can't necessarily turn a generic mesh data set into an SFA data set, but you can go from SFA to mesh. I've done this. I've got some examples later on if anybody wants to see them. Slightly more controversial, no, not controversial at all. Slightly more complicatedly, any raster is also one step back. We used rasters for two things. We use rasters basically as georeferenced images. A georeferenced image is a georeferenced image. That's not included in this definition. It's an image, not a data set. We also use rasters for data sets, like DEMS. This kind of raster is gridded data. It's data on a grid with a definition. The grid itself is a regular square, or even can be a triangulated mesh. Therefore, we can convert the gridded data directly into a mesh. We obviously can't necessarily convert any generic mesh into a grid, but we can convert any grid into a mesh. We can then add to it, because that mesh can then have data on nodes, data on edges, data on faces. We can define that, and we can add data to it. But we can also, every raster is a mesh. We can also have spatial networks and GMN. As I say, a mesh is a specialization of networks. Any generic spatial network can be converted into a generic mesh. It doesn't necessarily go the other way, because spatial networks have restrictions in terms of just say it doesn't necessarily go the other way. The quote there is from archaeology. Sorry, there's still a few archaeological quotes in there where they are using a lot of spatial networks to represent cultural change. So those are the three main data types. I hope so far I've suggested, not necessarily proved in 20 minutes, that we have three conceptual models of GIS data, all of which can be reduced down into spatial networks, which are intrinsically three-dimensional and much simpler to understand in 3 dimensions than the formats or the ontology we're using at the moment. There are other data sets which I've used this same understanding to analyze. So GPR data, I can show you later if somebody wants to. I can take you through the pictures. Is effectively can be very effectively represented as a spatial mesh and analyzed in that way. If you have a spatial mesh, you can do shape analysis on it. Shape analysis is a very well understood process from particularly medical imaging. You can also do network analysis on it. Network analysis is very well understood from more, mostly from social network engineering, but it brings a lot of tools. Some of which you already use, like Dijkstra, is actually a network analysis tool. All of which I could show you examples of all of those three. I actually left those in there, but I don't have time. So that is my theory. That is my theorem to you. We currently use an ontology based upon raster, vector, and to some extent GMN. This fundamentally limits our understanding and use of GIS data in true 3D analysis and in terms of virtual reality and true three-dimensional visualization of the data. There is a better representation, but there's a better representation that is intrinsically 3+1 and will make the move into three-dimensional data analysis and virtual reality a lot simpler for everybody involved.
Questions? Is part of the issue not that geospatial data uses planar coordinate systems rather than data in 3D, true 3D coordinate systems? Because my experience of working with AR and VR and those environments is that you need to understand the space that you're in, and our current data only understands itself relative to the map.
I'm now going to attempt to approximate the question first. You're saying is the problem really that most GIS data sets use two-dimensional coordinate systems rather than three-dimensional coordinate systems?
When we move to 3D coordinate systems, it's by reference to a 3D reference rather than being true 3D coordinate reference systems.
I would argue, although that's an important part of having a three-dimensional reference system, having the correct three-dimensional reference system is an important part of it. I would argue that our current understanding of data sets would still be wrong, or is still wrong, even when we have the correct three-dimensional data sets. If you look at rasters and vectors moving between projections, that is true even because we have, even with the three-dimensional coordinate systems, we have different three-dimensional coordinate systems. So we still have that problem. That problem is intrinsic to the representation and the ontology, not the coordinate system. I think if you'd asked me when I began this story, I would agree with you totally. My learning, having been through this story, is even though you get the coordinate reference coordinates correct, you still have the problem. Yes, sorry.
I was going to suggest a kind of different end of that same question in some ways, that about 3D at the global scale. A couple of things really. One is our kind of spherical coordinates, like kind of lat, long, and height, Euclidean, which was one basis that you had. But also, I was going to suggest maybe looking at what some of the MetaOcean people are interested in, the way they represent kind of 3D and meshes like this as well, might, because they've been there already because of having to represent kind of the Earth and that kind of thing.
To summarize the question.
2 parts. Is kind of global lat, long, height Euclidean enough to fit this model? And then the other suggestion was looking at what MetaOcean.
Yeah, is a global polar reference system Euclidean enough to solve this problem? And have I looked at what the MetaOcean people are doing? I'll answer the simplest part of that first. Is no, I haven't looked at what the MetaOcean people are doing. I'd love to talk to you about it. Part of the problem with polar coordinate systems, or certainly this is what we kind of came to in terms of discussing this with the archaeological people, is it has no if the dimensionality of your data set, the manifold dimensionality of your data set is 2 dimensions, then yes, it's good enough. If the manifold dimensionality of your data set is 3 dimensions, then no, you get into uncertainties about data position again, because you've got no definition of how the voxels move, voxel shapes change within as you go up and down the thickness. So again, it's this, you can solve it. As I say, all of these problems are solvable by adding definition upon definition. But if we're adding definition upon definition, what we're basically saying is the foundation is insecure. Whereas if we did have the mesh as the foundation concept, then all these problems would solve themselves.
Right.
Sorry.
No, I think that's probably all the time we've got for questions, but I'm sure Paul's around.
I'll be around
Lunch
later.
time, you
I'm
can ask
around
more
for the next
questions.
2 days, yeah.
Okay.